Hello, student. Welcome to this topic of time-dependent perturbation theory. In the last class, I have discussed the time-dependent perturbation theory in general, and I have derived an expression for the expansion coefficient of the time-dependent perturbation. So now, in this session, as an example, I am going to discuss the harmonic perturbation. So here we consider a system such as an atom or molecule exposed to harmonic perturbation such as electromagnetic radiation. That means we have taken here electromagnetic radiation as a stimulus to perturb the system because the electromagnetic radiation is a harmonic perturbation or the harmonic stimulus. So that is used here to make the system perturbed. The system is being an atom or a molecule. For convenience, we shall assume that the involved states are discrete. So that is important. Here I assume that for convenience, we shall assume that the involved states are discrete. A harmonic perturbation with the angular frequency omega has the form this h dash of r comma t is equal to 2 h dash of r into cos omega t dash. So the equation 1 clearly tells that the perturbation is an harmonic 1 because here the cosine term is there, which is a harmonic term. So therefore, the perturbation is a harmonic 1. But this cos omega t can be expressed as a cos omega t is equal to e raised to I omega t plus e raised to minus I omega t divided by 2. And substitute this into equation 1. So this equation 1 is the perturbation term. So the equation 1 becomes h dash of r comma t is equal to h dash of r into e raised to I omega t dash plus e raised to minus I omega t dash, and these two get cancelled. So this is the equation 2. The first order expansion coefficient is given by ck1 of t. So this is the first order expansion coefficient which is derived in the last session for the time dependent perturbation theory. So this one indicates that you are in the first excited state, and this is equal to 1 divided by I h cross 0 to t h dash kn or comma d dash and e raised to I omega kn t dash into dt dash. So this is the expansion term which is derived uh, for the time-dependent perturbation theory. So this term indicates that the state is there is a transition from state n to state k, and this one indicates that you are in the first excited state. Here h dash kn is the perturbation, and in this case it is given by. So this h dash kn r comma t dash is there. So this can be this we are writing in a direct notation as I explained in the last session. So this h dash kn is equal can be written as h dash kn. This is a matrix element multiplied by e raised to I omega t dash plus e raised to minus I omega t dash. And this matrix element I am writing in further short form as h dash kn, and this is multiplied to e raised to I omega t dash plus e raised to minus I omega t dash. So this is the perturbation term in equation 3. and substitute this perturbation term into equation 3. So equation 3 becomes the expansion coefficient. Equation 3 becomes ck dash of t is equal to h dash k n divided by h cross 0 to t and e raised to I omega t dash plus e raised to minus I omega t dash into e raised to I omega k t dash. This h dash kn is written out of this integral here. And now we have to multiply these two terms. Means we have to multiply this e raised to I omega k n t dash term to this bracket, so that the first multiplication gives e raised to I omega k n plus omega bracket multiplied by k dash. That means multiplying this term with this term gives this term plus multiplying this term with this term means second term with the this term common term gives the e raised to the I omega k n minus omega bracket multiplied by k dash into dt dash after multiplication. So here now I am integrating this equation. We have to integrate this equation. It is now the integrand is in the explicit function form, so it is very easy to integrate it. So you have to integrate term by term. So this is the first term, you will integrate it. So that gives this term e raised to I omega kn plus omega into t minus 1 divided by omega kn plus omega. So actually this e raised to I omega kn plus omega into t divided by omega kn plus omega you will get after putting the upper integral limit. And when you put the second lower integral limit, that means 0, so it is becomes e raised to 0. E raised to 0 is 1, 1 divided by this term. So it is 1, so 1 divided by omega kn plus omega is that. So this omega kn plus omega is LCM for these two terms, and this we got after integration. Just using the standard form integration integral of e raised to ax is equal to e raised to ax divided by a, that form is used here. And here also same thing comes, same. This term is also integrated. And here actually divided by I omega kn, it is actually divided by I omega kn plus omega is there. Here also I omega kn minus omega. That I is taken outside here. Here I is there actually. That I is taken outside and that I is multiplied to this I makes this I square, and I square is equal to minus 1. So in this way we got the negative term and negative sign in this equation 5. The first term on RHS of 5 has a maximum value when omega kn plus omega is equal to 0. This term, this is the first term. So this term is maximum when omega kn plus omega is equal to 0 or ek is equal to en minus h cross omega. Whereas the second term in RHS of 5 means this term. The second term is maximum. The second term is maximum when ek is equal to en plus h cross omega. So in other words, the effect of harmonic perturbation the effect of harmonic perturbation with angular frequency omega is to receive from the system or transferred to the system of or transferred to the system. That means here in this process, and a quantum amount of energy, that is S cross omega, is either given to the system or taken away from the system. So that is what happening here. The first term, the first one corresponds to induced or stimulated emission. The first term corresponds to induced or stimulated emission term. So induced or stimulated emission means already the atom will be in the excited state, because here CK1, as I told, this is the CK1 term. So this one indicates that already you are in the first excited state, and therefore the induced absorption term, this indicates induced first term indicates the induced absorption term, and that means already the atoms somehow will be excited to the first state, and they will be not coming down immediately to the ground state with an normal lifetime of 10 to the power minus 8 seconds. That means they will stay there for a little bit longer time. That means the time will be of the order of 10 to the power minus 4 second. Okay. So in order to make those transitions to come down, some stimulus is needed, so that we have to supply from external agency. So after taking that stimulus, those atoms will come down. Those atoms will come down to the ground state. So that is the meaning of stimulated emission. And whereas the second term corresponds to induced absorption or simply absorption. In case of induced absorption, the atoms will be initially in the ground state, and when you supply the energy externally to the system, that energy is absorbed by the system. That means that energy is absorbed by the atoms present in the ground state, and they will go to the first excited state. So this process is called as the induced absorption process, or simply the absorption process. Since only one term is important at a given time, we retain the second term and is given by. That means the second term is the induced absorption term is there, so that we are retaining here. So this is the second term of the above equation. That is the induced absorption term. I have written as it is. So this is the second term is written. So this the second term is adjusted in such a way that you see here e raised to I into bracket omega kn minus omega into t dot by 2 minus this term. This term is added and subtracted here. So, and when you multiply this term to this bracket, again we should get the same thing here. So that is possible. That is possible when you are dividing this term by 2. So that is why this adjustment I have made. So this 2 comes because I should get 1 here. I should get 1 here. When you multiply this term with this term, both the terms get cancelled. It becomes e raised to 0. So here you are getting 1. And here also it is balanced. Then Then this all these things are written as it is, and but this term in the bracket, that is e raised to I into omega kn minus omega into t divided by 2, minus e raised to minus I into omega kn minus omega into t divided by 2. This what we have added and subtracted. This term is written in compact manner as a sine of omega kn minus omega into t divided by 2 using the trigonometric functions. Next, if the system is initially in the state n, is initially in the state n, that is at the time t is equal to 0, the probability p from state n to k of finding the system in the discrete state k after a time t is ck1 of square. So the mod square, this is the mod square. The mod square of this term gives the probability of finding the state in the discrete state k. So that is why we have to mod square the equation 6, and the equation 6 becomes the probability of this function going from state n to state k is equal to is equal to this is 4, means I'm squaring this equation 6, it becomes like this. That is 4 h dash kn square divided by x square, and this is the square of the sine function, and divided by omega kn minus omega whole square is that, and this term that is e raised to I omega kn minus omega into t divided by 2, when you are squaring it, it becomes simply e raised to I omega kn minus omega into t, and this term goes unity when we are taking the mod square. So that is why we are left with this. We are left with this thing, that is p of n p n k of t is equal to mod of ck1 square I is equal to 4 h dash kn square or h square into sine square of this function divided by omega kn minus omega into whole square. An interesting feature of the result is that the transition probability oscillates sinusoidally as a function of time. The probability p from n to k versus omega kn minus omega plot is as shown in the figure. So this is the plot. That means at k is equal to at this quantity. That means when omega kn minus omega is equal to 0, the probability of finding the particle becomes maximum or unity. So at this state, that term e raised to I in the above equation, as I explained, e raised to I omega kn minus omega into t divided by 2 goes unity because of this reason. So at this quantity, that is omega kn minus omega bracket square is equal to 0, he becomes at that condition, this probability of finding the system in the state k becomes a maximum, and as this value increases, the probability going down. So that is shown in the diagram. So the central peak has a height of this thing, that a height of this h dash kn square t square divided by x square. The peak, the central peak, or height of the central peak is given by this equation, that is h dash kn square t square divided by x square. and a width of about 2 pi by t, and and it is having the width of about 2 pi by t, and therefore the area under the main peak is proportional to t. The area under the main peak is proportional to t, means time. So as the time passes, uh, the area under the curve also goes down. And when t crosses the given time, t becomes 0. That means area becomes 0. So that means the probability of finding the system in the state k beyond the time t is a 0. That is that is the probability of finding the system in state k is proportional to the time t. So this is very important. That means here the perturbation on the system will be existed only within the time t is equal to 0 to some time t. Before t is equal to 0 means before start of the perturbation, before switching on the perturbation means actually we are switching on the perturbation at the time t is equal to 0. So that is why before t is equal to 0, the system is initially in the state n, and from t is equal to 0 to some time t, the system will be in the state k, and beyond this time t again the system will be some other state or in the ground state. So it may be noted that the probability of finding the system in a state whose energy differs considerably from the initial state En is smaller than the probability of finding it in a neighboring energy state. So this point is very clear now that the probability of finding the system in a state whose energy differs considerably from the initial state En is smaller. That means we initially, as in the beginning, I told that when you study the perturbation, uh, we assume that this perturbation term h dash is very very less than h naught, the time independent term. So that is the limitation of this perturbation theory. That means the perturbation should not be more. It should be within the limit, small limit. Then only we can study this thing. That means when the energy changes slightly around this En, then only it is possible to find the system. Otherwise, no. So this is an example for the time dependent perturbation theory. I took as an harmonic example. So thanks for watching.